Good morning, everyone. My name is Nandita Singh. I'm from EC department and I'm doing my master's in computer engineering. And today I will be presenting a paper on designing and implementing malicious hardware. Whenever we talk about hardware, we have to realize that we are talking about a low-level part of the system, which is like the final destination for all the data which is given from the software. So here, this paper is focusing on basically implementing a hardware which kind of supports an attack. So we have seen a lot of attacks in happening in the security community. Most of them are software attacks. And at the software level, we have a lot of antiviruses because we have attacks. But nobody has ever explored what if we make the hardware vulnerable. Making a hardware vulnerable is not just letting the attacker having the entire control of the system, but is also making any antivirus ineffective. Because at the end of the day, all the antiviruses, all the softwares, in fact, even our OS system is stored in our hardware. So this kind of implementation is very dangerous, and that's what the gist of the paper is, and that's what they have proven in this paper. So moving ahead, I think the motivation of any paper comes from a good story. So the story is real and it starts from 1982 when the USA was having a Cold War. So at that point of time, the CIA kind of sabotaged the oil pipeline software and let the Russian spies take that software and use it in their area. So they have used those software, and in January 1982, they had like a big trigger in that software, which led to a big explosion. So that how the attacks can be dangerous. Like this is the biggest example how a software attack can actually disrupt such a big hardware. And on the other way, the other example show us how an hardware can, can be above everything. Like in today's world, the most important thing is data. If the data is leaked, if any information is leaked, it is like the biggest threat to anybody. So this thing happened in 2005 when the typewriter in the US Embassy in Moscow was kind of altered, and the Russians were able to actually get all the information which was starting or had a word, a magic word. So whenever there was any document which used that magic word, the entire document was able to be decoded by the Russians. So this happened in 2005. And we cannot forget about what happened with Apple iPods in 2006. So there's this virus, RAV-MON-E. So this particular virus is generally, or we can say more popular in Microsoft's or Windows. But in 2006, Apple iPods, they were infected by this virus. And we know that Apple is never alone. It's not just one entity because Apple is about the entire ecosystem. So if you have an iPod, you have an iPhone, iMac, everything is connected. So this particular virus, what it do is like it will get your personal access, it will get the control over your system, and once it get the control of your iPod, it can basically can control your entire Apple ecosystem. So this happened in 2006, which led to a lot of losses for the company. And that's how some changes in the hardware, some exposure of a virus in a hardware can lead to such big losses. So we have seen like a security loss in terms of security of a country. We have seen the losses in terms of your personal breach of privacy, and the list goes on. And this is like the fourth example, which was about selling hard drives by Seagate in Taiwan. So this had a Trojan attack, which kind of makes the remote attacker enable to get all the personal information about the person using the hardware. So they were selling these hardwares in Taiwan, and a lot of personal information was exposed to a lot of attackers. So these were like the few examples that we have seen, and we can know like how the attacks can be dangerous, and we know like the entire security community is trying to prevent those. So till now we only have most of the focus on having the viruses and antiviruses at the software level. Nobody has actually explored what happens if the entire hardware becomes vulnerable. What happens if the hardware is, you know, facilitating the attacker to do an attack. So, if we talk about software, any of our application or any of our website is installed in the hardware, and if we are doing any uh, action for even just like pressing a tap a touch button in our phone, the entire data is basically sent to the hardware in terms of zeros and one, and then the processor process that information and then tells what to do next, again back to the software. So in any system we have like these three layers. We have the software, which is like the user interface from where we are making all these applications and whatever we can see on our computer, that is the software. And then we have like a mediating layer, which kind of acts as an interaction between a software and the hardware. And then we have the hardware. So the mediating layer basically converts the software data into bits, bytes. We have the compilers, linkers, and then sends the data to the hardware. And hardware is the key. It's like the backbone of the entire system, which basically which gets all the information and then kind of process it what to do next. And it kinds of give the command to the entire system how it should behave. So if there is any hole in the hardware, or if there's any implementation in the hardware which is in favor of an attack, then even the software and any antivirus that is installed for software detection cannot comprehend that danger. So, in this paper, they have basically implemented two malicious circuits. So before all the examples that we have seen, none of them have actually implemented malicious circuits at the HDL level. They just have done, but they do had like some malicious components in the device, which has led to those attacks. But in this paper, they have claimed and proven to be the first one to make two circuits, which are basically which can give access to a pseudo attacker to do these three attacks. So one is the privilege acceleration attack, the other is the login backdoor, and the third one is service to steal password. So the first technique that they have used in this paper is memory access mechanism causing privilege acceleration to root. So generally, like we have seen in our terminals, if we are working, whenever we are trying to install any application or do anything, it always asks for sudo permission. So the sudo permission is the root permission, that only if you are the valid authorized person, only then you can install a specific application in your system. So those are the root permissions, which needs like a username and the logins. But by using this technique of memory access mechanism that they have used, they have kind of got the root access without even having the credentials. So this is one of the general purpose pictures that I have taken to actually explain what they have done. So these are the processes which is coming from the CPU to a memory management unit. So the two circuitries that they have implemented in a processor, Leon 3. So this processor comes along with a memory management unit and physical memory. So what is happening is, in the processor has given some instructions, and we generally have some data lines, we have instructions line. So in their mechanism, what they are doing, uh, okay, so there's one more thing that I wanted to say is the assumption in this entire paper is that whatever hardware that we are using have like a network interface. So network interface means they will have some serial buses like UART, Ethernet, and SPI or I2C interface, so that we can get the data from the external environment. So what they have done is that on their data caches, they are sending a sequence of magic bytes. And in their memory management unit, they have like a FSM state, which kind of detects those bytes and tells the memory management unit to kind of give all the privilege access to the entire memory. So when the entire memory is being exposed, even the privileged area, then the OS internal memory is also get exposed to the attacker, by which they can, misuse it, and they can just turn off the protection and turn off any checks to the malicious firmware, and that's how they can get the entire access to the system. So this is like one technique that they have used. The other technique is the shadow mode. So using the shadow mode technique, they have implemented two different attacks, that is login backdoor and stealing passwords. So if we see in this particular diagram, they have a core, a normal mode, a normal cache, whereas they also have a shadow memory. So this is a ISA level attack. In the ISA level, they have like a shadow instructions uh, and a shadow memory, which are like kind of invisible to the CPU. So there will be a bootstrap which will have some piece of code, and they will be waiting for a trigger. Again, from the external serial buses, whenever a sequence has been passed, the bootstrap gets triggered and kind of stores the entire firmware in this shadow memory. And then the core execution goes to the shadow memory, and then it starts executing the malicious firmware. So the entire system has been attacked just by the hardware, just by sending some bytes with some payloads, and we were able to attack the entire system. So if we see in the next slide, this is like a little bit overview how this attack has taken place. So let's say we have this UDP packet that we have sent, and we have some magic bytes, malicious firmware, and UDP header. It comes, the monitors notice that magic sequence, and instead of discarding, like, because since it's not a robust hardware, rather it's like somebody who's facilitating to an attack, it will see the magic words, it will actually store the entire corrupted, not the corrupted firmware, but the malicious firmware in the shadow memory, and then triggers that shadow memory. Now, what this malicious firmware do is that it kinds of return the value of the password as true, no matter what the password you are giving. So in that way, from the back door, we are able to log in into the system, even without actually knowing the correct password. So if you just say, let me in, it's just going to return a true value, because the firmware which has run has that malicious code, and we can get the access of the entire system. So this is the another attack that they have done. And there's about one more attack which they have mentioned is the stealing password. So about that, I would like to give you an idea how they have done it. So basically, at the hardware level, in the memory, in these memories, we will have like a swarm of data. Everything will be in the zeros and one. So what their entire concept is based on the user's last login. But with the swamp of data, how can we actually find out the password? That is like a really interesting question which came to my mind, and I would really want you guys to brainstorm on that. That when we have just the series of bits and bytes, and how can we actually know, like, okay, this is what we are looking for? So this is something that they have actually implemented, and which is very interesting. And they were able to retrieve the actual password of the user. So in that way, also they were able to just log in from the actual ID and the password, and can get access to the entire system. So that's a really interesting domain, and like something really interesting question to get the answer about. Um, and after all these implementation, these are the results that they have. So if we see like the baseline CPU and the baseline CPU with the two malicious circuitry only have like very minimal line of codes, very minimal line of logic gates. So I think this particular slide shows in terms of the actual numbers, the evaluation. So we have like 68 lines for memory access mechanism, which are more than the actual CPU, 117 lines for shadow mode mechanism. Even in terms of logic gates, the logic gates are very minimal. Like if we are going to convert any RTL into the gate level, minimum for a processor, it's like 1 billion. So compared to 1 billion, the number of logic gates which were used extra were very less. So even if we see the percentage wise, it's like 0.05 and 0.08 increase in the logic gates, which will not be like very much, costly to implement. And also they have like claimed that from the gate, if the attacks are more and if somebody tries to reverse engineering their circuit, they can do that, but it will be very time consuming and can cost up to like $250,000. So they have like a robust little circuit in the processor, which is actually creating a lot of attacks. And I would also like to mention that in a core, generally, the state space is really large. So in such a big, large state space, when a little bit FSM states have been added, or if a little code of line is added, it is very difficult and challenging to actually pinpoint like which piece of code is prone to any software attack. And this is timing perturbation results that they have. So we can see on the y-axis, we have the timing. So let's say if the CPU is working at its full efficiency, it's given as 1. And then they have shown the overheads. And on the x-axis, they have their benchmarks. So these are the CPU bound and the IO bounds benchmarks that they will be running in the CPU while they'll be using those attacks. So from this bars, what we can see is the baseline bars, which is denoted by black bars. These are the bars which is like running the CPU in like normal condition without any hardware change and without any attacks. So that is the baseline for our measure for this measurement. And then is the known root. So known root is like the best case scenario for an attacker. So where the root is being known to the attacker, like the credentials for the root access is known to the attacker, and then they're just attacking in the system. So that is shown with the blue. With the green is the transient. So when these benchmarks have been running, during that benchmark, we are trying to do a backdoor access, and we are able to do that backdoor access with this much amount of timing overhead. And then the persistent one denotes that we are like continuously trying to do backdoor login while we are running these applications. So we also have the overheads in this particular slide. So these were the results of this paper. And the conclusion is that they have actually targeted the hardware. And once you have targeted the hardware, it is very difficult to actually save any software attacks, because it kind of makes the software attacks invisible to the antiviruses. So it's just put it in the shadow mode. It will just save it in the shadow memory. It will start executing there. The core will never know, the software will never know what is happening in the system. And that's how the systems can become highly vulnerable. And it's very, very dangerous. And I also after reading this paper, I also were looking into like the future scope and like how this paper can change the entire vision that we have for design verification, because we have designed a circuit which is actually facilitating to attacks. So we also need to have a mechanism to prevent it. So like even now the industry is more focused about the actual functioning of an design. Now the industry is also exploring the sites where they can see if there's any circuit which can make the system more vulnerable, or we can make any circuit which can make the system robust by detecting these kind of FSMs, by detecting these kind of attacks or these kind of vulnerabilities in the circuit. So I think that's the future that this paper has shown us. And in the future scope, I think the person who can make the bug can also solve it. So I think the circuits that they have used can be analyzed and can be used to make more robust systems by having the FSMs which can detect the systems which are trying to have the access to the privileged area, and then can just make the entire system go into a fault state or in a trap state. So those kind of future work can be done on this. And that is something that I thought about, but I'm really sure that you guys would also like to brainstorm about this topic and see what good ideas can pop in. So that's all for me. Thank you very much. And these are all the references that I have used to get all these pictures. Thank you.